In this section, we're going to look at how acid derivatives can be converted into other acid derivatives by the appropriate reaction. For example, if we add water to any acid derivative, we can turn it into a carboxylic acid. If we add an alcohol, we can turn it into an ester. If we add an amine or ammonia, we can convert it into an amide. We'll also look at reactions with nucleophiles such as a Grignard, which will convert an acid derivative generally into a ketone initially and then into a tertiary alcohol, after the reaction occurs again. Acid derivatives can also react with hydrides to be converted into aldehydes, which generally will be reduced further into an alcohol. Okay. We're going to look at a number of acyl substitution reactions. It's important to remember that in acyl substitutions, a nucleophile is replacing the leaving group. And so you should be able to recognize this pattern and be able to predict the product once you know which nucleophile you're using. And it doesn't matter which acid derivative we're using, since the product will be the same and be primarily based on the nucleophile we're using. The leaving group will then be eliminated as a byproduct, and so the byproduct will always be dependent on whichever leaving group we have on the acid derivative. So keep that in mind as we go through these many examples so that you're not overwhelmed as far as predicting the product from each reaction. We're going to start off with hydrolysis reactions, meaning the addition of water to different acid derivatives. And we're going to do this in a sequence where we start with the most reactive acid derivative, which is the acid halides. An acid chloride, for example, can react with water to become a carboxylic acid. So the water will add to this carbonyl and kick out the chlorine, and so you'll have a hydroxyl group there and therefore form a carboxylic acid. As a byproduct, the chlorine will become ACl. Here's a look at the mechanism. Water can add to the carbonyl, break the double bond, give us a tetrahedral intermediate, which then reforms the carbonyl, eliminates the leaving group to give us this protonated carboxylic acid, which then loses a proton with base to become a carboxylic acid. Acid chlorides and even acid bromides are so reactive that this reaction can be done under neutral conditions. So water, although it's not the greatest nucleophile, it's a good enough nucleophile to react with this very hot electrophile. Acid anhydrides are very reactive, not quite as reactive as an acid chloride or an acid bromide, but they're quite reactive enough that they can react directly with water without the need of heating or an acid catalyst, for example. So water can add to an acid anhydride. So the water would add to one of these two carbonyls, and it doesn't matter which one you pick first. It will lead to an acyl substitution that turns these anhydrides into two carboxylic acids. So if you break the anhydride in half, you'll turn the left side into a carboxylic acid, the right side into a carboxylic acid, and so you'll have benzoic acid and acetic acid. Note that this reaction is the reverse of the reaction we saw earlier, where we took two molecules of a carboxylic acid or two different molecules, and if we heated them, we would get an anhydride plus a water byproduct. Here's a look at the mechanism for this reaction. So water adds to one of the two carbonyls, and again, it doesn't matter which one. It'll give us a tetrahedral intermediate. Water or some other base will remove one of these protons from the water they just added, giving us this product or this intermediate. The oxygen of what used to be the carbonyl will reform the carbonyl, eliminate the leaving group, and give us the two carboxylic acids. Now, esters and amides are less reactive than anhydrides, and so to hydrolyze esters and amides, we need to typically step up our reaction. We need to either heat the reaction or use an acid catalyst or do both. An ester can be hydrolyzed under acidic conditions. So if we add water to an ester, NaCl, we can hydrolyze this ester bond and turn the carbonyl into a carboxylic acid, and the alkoxide group here on the ester is eliminated as an alcohol. Now notice this reaction is the reverse of the Fischer esterification reaction. In the Fischer esterification, we started with a carboxylic acid and an alcohol, added ACl to get an ester and a byproduct of water. Here's another example. Here is ethyl benzoate. We add water and ACl. We can hydrolyze that ester into a carboxylic acid and ethanol. Let's take a look now at the mechanism for the acid-catalyzed ester hydrolysis. Starting off with an ester, if we add an acid catalyst, or if you want to use the hydronium ion, which is the result from an acid reacting with water, either way, we can protonate the carbonyl. We now have a protonated carbonyl in the next intermediate. It's a better electrophile than the ester we started with. Water can then add to the carbonyl, break the double bond, give us this tetrahedral intermediate, and then water can remove this proton, form a double bond, a carbonyl, by eliminating the leaving group. That gives us the carboxylic acid, an alcohol, and then a byproduct of the hydronium ion, which starts the cycle once again. So this is our acid catalyst in this mechanism, and it starts the cycle again. Amides are the least reactive acid derivative that we'll talk about in this chapter. And amides in general, in order to be hydrolyzed, need to be not only treated with an acid or a base catalyst, we also usually have to heat the reaction as well. Here's an example with an amide. If we add water and HCl, we have to heat it to hydrolyze that amide into a carboxylic acid and an amine. The amine comes from the leaving group on the amide. The carboxylic acid comes from the water adding and replacing the amine leaving group on this carbonyl. Here's another example, another amide is hydrolyzed with water and HCl by heating. It is turned into a carboxylic acid and the appropriate amine. The mechanism for this reaction starts by the carbonyl of the amide being protonated. Then water adds to the carbon of the carbonyl, breaks the double bond, gives us a tetrahedral intermediate, which then loses a proton as shown here. So water removes this proton, forms a carbonyl, eliminates the leaving group. It gives us a carboxylic acid plus an amine, or in this case an ammonia molecule as a byproduct. Esters and amides can also be hydrolyzed under basic conditions, and we're going to refer to this reaction as a base promoted reaction because the base is actually consumed in the reaction and it is not acting as a typical catalyst which is regenerated. So under acidic conditions, the acid is a catalyst. Under basic conditions for hydrolysis of esters and amides, the base is actually consumed, and so we consider that a base promoted reaction. Starting off with the ester hydrolysis, Under basic conditions, we would use sodium hydroxide or some other base plus water. And then since the reaction leads to a carboxylic acid, which is acidic, and we're using basic conditions, we have to use a second step, which involves a small amount of acid that neutralizes the base plus protonates this carboxylic acid. And so anytime any reaction leads to a carboxylic acid as a product, and the reaction is done under basic conditions, we always have to use a second step of acid. So this reaction not only produces a carboxylic acid, but also an alcohol. So the alkoxide group on the ester is eliminated as an alcohol, so we get ethanol in this example. Here's one more example. Under basic conditions, the water will add to this carbonyl and turn it into a carboxylic acid, which is shown here. And then the leaving group becomes an alcohol. So this is propanol. That's eliminated, and you see that in the product. Here's a look at the mechanism for ester hydrolysis under basic conditions. So the hydroxide ion is a very good nucleophile. So unlike water, when we add water to an ester, we have to protonate it first, since water is a poor nucleophile. But the hydroxide ion is a very strong nucleophile, so it can add directly to the carbon. It breaks the double bond, gives us this intermediate, this tetrahedral intermediate. The carbonyl reforms by eliminating the leaving group, the alkoxide group on the ester. We end up with a carboxylic acid initially. We get a leaving group here, which is an alkoxide ion. Now, because the reaction is done under basic conditions, usually this carboxylic acid is deprotonated. It turns into the conjugate base. And so we have to use aqueous acid in the last step to return back to the carboxylic acid. Amides can be hydrolyzed under basic conditions as well. Typically, this reaction is done by heating the reaction, since amides are relatively unreactive compared to other acid derivatives. So as an example, if we take this amide, we can hydrolyze it with sodium hydroxide, water, by heating. So this carbonyl becomes a carboxylic acid, which is propanoic acid. The amine leaving group is eliminated as an amine, so we end up with a primary amine. Now notice this reaction has a second step of aqueous acid. The reason for that is, since we're producing a carboxylic acid, which is acidic, and we're doing it under basic conditions, we have to use aqueous acid at the end to neutralize the base, plus turn the conjugate base of the carboxylic acid into a carboxylic acid. Here's a look at the mechanism. It starts off with the hydroxide ion attacking the carbonyl carbon, breaking the double bond here, giving us a tetrahedral intermediate. The carbonyl reforms by eliminating the amino group. That gives us initially a carboxylic acid, but because this is done under basic conditions, the carboxylic acid is deprotonated and turned into a carboxylate ion. For this reason, we have to use aqueous acid as a second step to add a proton back on the carboxylate and end up with a carboxylic acid at the end of the reaction. Earlier in this chapter, we saw a reaction involving ester hydrolysis under basic conditions to make a carboxylate ion, and then if we added aqueous acid as a second step, we would make a carboxylic acid. Now that reaction is often referred to as a saponification reaction because the reaction is traditionally used to make soaps. So soaps are made by taking a fat which is essentially a triglyceride. So triglycerides are made from taking 3 fatty acids or perhaps 2 fatty acids and a phosphatate group attached to a triglycerol molecule. So triglycerol has 3 carbons and 3 alcohols on those carbons. If we add sodium hydroxide or potassium hydroxide, we can hydrolyze these esters, as we've seen before, into an alcohol, or actually a triol, and 3 molecules of these carboxylates. Since the esters here are formed from fatty acids, so triglycerides involve 3 fatty acids, or sometimes 2, the product that we get here would be the conjugate base of a fatty acid. So soap is simply a sodium or potassium salt of a fatty acid. And again, that's typically made from taking a triglyceride and adding a base plus water and hydrolyzing the ester bonds. An example of a soap molecule would be sodium stearate, which is the sodium salt of a fatty acid. Now, there are many soaps that are sold commercially, and each one will have different properties. Some are liquids, some are solids. They'll be a little bit more slimy than others. All of that depends a lot on the molecule that we make it from. So the triglyceride source will give you different salt properties. Also, using sodium versus potassium hydroxide will give you slightly different properties for the soap that we make at the end of the reaction. We're going to try to convert N-ethylbenzamide into benzoic acid. Amides can be converted into carboxylic acids through a hydrolysis reaction. The hydrolysis reaction of amides always has to include an acid or a base catalyst, and it has to be heated. So as an example, we can convert N-ethylbenzamide into benzoic acid by adding HCl, water, and heat to do the hydrolysis reaction. A second way we can do this reaction would be under basic conditions. So for example, we could use sodium hydroxide, water, and heat. Now, any reaction that leads to a carboxylic acid and is done under basic conditions has to involve a second step where we add a little bit of acid. So we could abbreviate that by just simply add hydronium ion. The hydronium ion would neutralize the sodium hydroxide. It would also convert the conjugate base of the carboxylic acid into a carboxylic acid. So there's 2 ways you can do this hydrolysis reaction, as you see here, under acidic or basic conditions. Derivatives will react with alcohols to make esters. For example, an acid chloride, which is very reactive, can react with an alcohol at room temperature to produce an ester. In this example, notice we're using pyridine. The role of pyridine here is to soak up or react with the HCl byproduct of the reaction. Since we're using an acid chloride, that chlorine eventually picks up a proton and becomes HCl. In the second example, we're using a diol. The diol has a primary alcohol and a secondary alcohol. Primary alcohols in general are more nucleophilic than secondary alcohols since they're less hindered. And so if we were to use one equivalent of an acid chloride or any other acid derivative, the reaction will occur through the primary alcohol. So as this example illustrates, we form an ester from the primary alcohol, and notice the secondary alcohol doesn't react. Now, if we use enough acid chloride, the secondary alcohol will become an ester as well. Alcohols can react with acid anhydrides to be converted into esters. As an example, we have here a primary alcohol mixed with acetic anhydride and a small amount of pyridine. The pyridine helps to remove the proton on the alcohol and make it more nucleophilic, and as a result we get an ester. Now notice half of the acetic anhydride will be eliminated as a carboxylic acid or acetic acid in this example. In the next example, we have a diol involving a primary alcohol and a secondary alcohol. When we use only one equivalent of the acid anhydride, only the primary alcohol is converted into an ester since it's more nucleophilic. The other half of the anhydride will become a carboxylic acid. The secondary alcohol will remain unreacted, and if we were to use enough of the anhydride, 2 equivalents or more, we can convert that secondary alcohol into an ester as well. Alcohols are more nucleophilic than the carboxylic acid hydroxyl group. And so in this example, if we use an acetic anhydride, only the alcohol is converted into an ester. As a side note, esters are sometimes used as protecting groups for alcohols. Addition of an alcohol to an ester can lead to a reaction called transesterification, which is the conversion of one ester into another type of ester. As an example, if we start off with ethyl propanoate and we add HCl and methanol, we can exchange the alkoxy groups on the ester into a different one, in this case methoxy. So the methanol will add and replace the alkoxy group already on the ester. Now notice this reaction is done under acidic conditions, so that's typical for transesterifications. Since esters are relatively unreactive, unlike acid chlorides and acid anhydrides, which can react at fairly neutral pH with an alcohol, esters require usually mild heating and usually an acid catalyst or a base catalyst for the reaction. Here's an example of an intramolecular transesterification. If we have a molecule that has an alcohol and an ester, we can add HCl to help the reaction. So the HCl will protonate the carbonyl. That would allow the alcohol to attack the ester and cyclize this molecule and give you a cyclic ester, which we refer sometimes as a lactone. The alkoxy group, which in this case is a methoxy group, will be eliminated as an alcohol, a methanol molecule. Also do a transesterification reaction under basic conditions. This is referred to as a base-promoted reaction since the base is generally used up in the reaction and it's not your traditional catalyst. Whatever alcohol we want to add to the ester, we typically take the conjugate base and use that as a base. So for example, if we wanted to add methanol to this ester, we would use the conjugate base of methanol, which would be a methoxy group, to act as the base. Just like the acid catalyzed reaction, we want to heat this reaction since esters are relatively unreactive. And notice in this reaction, we're changing the ethoxy group for a methoxy group, therefore doing a transesterification reaction. The ethoxy group, which is eliminated as an alcohol. So in this case, we get an ethanol molecule. Here's an example of an intramolecular reaction between an alcohol and an ester. So the alcohol will cyclize on this ester and form a cyclic ester, a lactone. Aspirin, as we probably know, is an anti-inflammatory and fever-reducing drug. It was originally isolated from the bark of the willow tree, and nowadays is typically made in a lab. Now, aspirin is responsible for reducing inflammation and reducing fever by inhibiting the action of an enzyme called cyclooxygenase, which is usually abbreviated as COX or COX enzyme. The way that aspirin inhibits the COX enzyme is by transferring an acetyl group to the serine amino acid and found in the active site of this enzyme. So a serine group has a primary alcohol as a side group, and aspirin looks or has a structure like this, which includes an acetyl group or an ester group. The alcohol, the primary alcohol from the serine group from the COX enzyme will attack the acetyl group of aspirin and essentially do a transesterification reaction to transfer the acetyl group onto the serine. This inhibits the action of this enzyme and therefore leads to the reduction of inflammation as well as the reduction in fever. There's an enzyme in our bodies called pancreatic lipase, which is responsible for breaking down triglycerides into fatty acids, as well as a monoacylglycerol molecule. Now, this pancreatic lipase has a serine group in its active site containing an alcohol that is nucleophilic, and certain anti-obesity drugs such as orlistat are composed of a beta-lactone, which is a cyclic ester containing 2 carbons in addition to the ester group. This is a very reactive ester, so most esters are relatively unreactive towards nucleophiles, but when you put the ester in a small ring, such as a 4-member ring, that ester behaves more like an acid chloride in terms of reactivity, and it will react with the serine group of pancreatic lipase and therefore inhibit the action of that enzyme. As a result, these anti-obesity drugs stop the breakdown of fatty acids, and triglycerides, instead of being digested, will simply go undigested to the digestive tract of a person. In this question, we want to look at the mechanism for the following nucleophilic acyl substitution reaction. So this reaction involves an acid chloride, a methoxy nucleophile, and methanol to become an ester. This exact example was actually not covered in this section, but is one that we should be able to come up with a reasonable mechanism based on the other examples of acyl substitution reactions we saw in this chapter. So in this reaction, we're using a base to do an acyl substitution on an acid chloride. So the reaction should work by the base, the methoxy group, attacking the carbon of the carbonyl of the acid chloride, breaking the double bond to form a tetrahedral intermediate, and then the oxygen reforming the carbonyl by eliminating the leaving group. In this question, we have a functional group that we did not see in this chapter react with different nucleophiles. So this is a cyclic anhydride. and we want to react it with one equivalent of methanol. Now, we saw examples in this chapter of anhydrides reacting with methanol, so we should be able to come up with a reasonable product based on those examples. As we saw in some of the examples in this section, alcohols add to acid anhydrides by an acyl substitution. And so in this example, we have simply a cyclic anhydride. So we should see a similar reaction. If we use one equivalent of methanol, then the alcohol should add to one of these carbonyls, either one. In this case, it would not matter since the anhydride is symmetrical. And that would lead to breaking this oxygen bond here, so eliminating this, right? And half of the molecule, in this case the bottom half, would become a carboxylic acid. The top one would become an ester that involves the methanol being connected to a carbonyl. In this question, we want to predict the reactant, and specifically the acid chloride that we would need to use in order to make ethyl benzoate through an acyl substitution reaction. In a way, we also need to predict which alcohol we need to use as well. In order to make ethyl benzoate, we need to think about which acid chloride and which alcohol we need to use. In order to figure this out, we want to break this bond between the carbonyl and the ethoxy group and turn the carbonyl into an acid chloride, which would mean we would need to use benzoyl chloride. We would also need to convert this ethoxy group, the leaving group, into an alcohol that we would use as a nucleophile. And so the alcohol that we would need to use would be ethanol. Amines are fairly good nucleophiles that can react with different acid derivatives to make other acid derivatives, specifically amides. If we start off with an acid chloride and we add 2 equivalents of ammonia, we should make a primary amide. One of these ammonia molecules would replace the chlorine and give you an NH2 group on the carbonyl. The other molecule of ammonia will react with the ACl byproduct that results from any acyl substitutions on an acid chloride and would form a byproduct of ammonium chloride. In the next example, again, we're using an acid chloride, benzoyl chloride to be exact. We have to use 2 equivalents of an amine. One will replace the chlorine and give you, in this case, a tertiary amide. And the second molecule of the amine will react with ACl to give you an ammonium byproduct. Note that we can use just about any amine or ammonia derivative in this acyl substitution, and any other acid derivative would work the same way. However, tertiary amines are not generally used for this reaction. In fact, they're usually not used as nucleophiles since the nitrogen already contains 3 alkyl groups. It doesn't like to add to electrophiles since it would lead to forming an ammonium product, which has 4 groups on nitrogen with a positive charge on the nitrogen. So generally, tertiary amines are not used as nucleophiles in not only acyl substitutions, but other types of reactions. As a side note, amides are sometimes used as protecting groups for certain amines. If we have a primary amine, we can react it with an acid anhydride, such as acetic anhydride, and form an amide, as well as a byproduct of a carboxylic acid. So half of the acid anhydride will be eliminated as a carboxylic acid after the nitrogen has attacked one of the carbonyls and eliminated that carboxylic acid. Note that amines are in general more nucleophilic than alcohols. So if you had a molecule that had both an amino group and an alcohol group, if we use only one equivalent of an acid uh, uh, derivative, whether it's an acid anhydride or an acid chloride, the reaction would always occur through the nitrogen. And so you can see that the product contains an amide bond rather than an ester bond. Now, if we use enough of the acetic anhydride or any other acid derivative, we could also form an ester from the alcohol. Esters can react with amines such as ammonia to form amides as well. Now, generally, esters are less reactive than acid anhydrides and acid chlorides, so we usually have to heat the reaction. And here's an example with methylbenzoate reacting with ammonia to form benzamide, as well as a methanol molecule byproduct. So the byproduct comes from the leaving group of the ester, and then the amide forms from the ammonia, adding to that carbonyl to give you this primary amide. Here's a second example with a primary amine. It replaces the ethoxy leaving group, which becomes an alcohol, an ethanol. The amine, once it adds, it forms an amide, a secondary amide. This reaction could occur intermolecularly, and that would be true for any acid derivative. So the amine would add to the ester, eliminate the leaving group, which becomes a methanol molecule. In the process, we form, in this case, a six-member cyclic amide. Cyclic amides are referred to sometimes as lactams. And lactams are actually very important in the chemistry of antibiotics. Specifically, many antibiotics, such as penicillin G, have a four-member cyclic amide. This is called a beta-lactam, since it contains two carbons in addition to the amide. Beta-lactam antibiotics such as penicillin were among the earliest discovered antibiotics. Penicillins were originally discovered as from a mold growing on a cantaloupe back around the 1930s, and then it was developed into an antibiotic eventually in the 1940s. Antibiotics are one of the main reasons why the life expectancy of humans has drastically increased from the 1940s until now. Beta-lactam antibiotics work by inhibiting an enzyme called transpeptidase, which has a serine group with a hydroxyl group attached in the active site of this enzyme. Now, the enzyme is responsible for the synthesis of bacteria cell walls, and that serine group will generally react with the carbonyl of beta-lactam and connect to it through a ester bond, and therefore the enzyme is inhibited. Now, in general, amides are fairly unreactive, but when they're placed in a small ring like a beta-lactam, they tend to react more like an acid chloride, and so they're extremely reactive towards nucleophiles such as an alcohol. We want to prepare propanamide using an acid chloride and an amine or ammonia. So attempt to do this problem before you look at the next slide. So to answer this question, we want to convert propanamide into an acid chloride and amine. In order to do that, we should imagine replacing the amino group with a chlorine. That would give us propanoyl chloride. The amino group, in this case, is NH2. If we add a hydrogen, we come up with ammonia. So that would be the amine that we want to use. Carbanions such as Grignards and organolithiums add to acid derivatives such as an acid chloride to make tertiary alcohols. As an example, an ethyl organolithium will add to an acid chloride to add 2 ethyl groups and give you a tertiary alcohol. We could do the same thing with a methyl Grignard, which will add a methyl group to benzoyl chloride to initially give you a ketone. But as we know, ketones also react with Grignards and organolithiums. And so instead of isolating the ketone, typically we will get an alcohol, a tertiary alcohol as a product. Also react with Grignards and organolithiums to make tertiary alcohols. As an example, phenyl Grignard will add twice to methylbenzoate to give you triphenylmethanol. So 2 new phenyl rings are added to the carbon that used to be part of the ester. An organolithium will do the same thing to an ester to give you a tertiary alcohol that has 2 ethyl groups added. Organocuprates will add to acid chlorides, and instead of doing an addition, they do generally a substitution reaction. So an acid chloride as shown here will react with a Gilman reagent to make a ketone. Here's another example with an acid chloride. If we have a Gilman reagent that has a pair of ethyl groups, one of those ethyl groups will be transferred and the chlorine will be replaced by an ethyl group. In this last example, a Gilman reagent with methyl groups will substitute a chlorine on an acid chloride to give you a methyl ketone. Note that this reaction is specific to acid chlorides. Other acid derivatives like esters, amides do not undergo this type of reaction. In this question, we want to predict the ester that we would need to start with in order to do a Grignard reaction and make the following alcohol. To answer this question, we want to look at the alcohol that we're going to end up with and think about what ester and what Grignard reagent we would want to use. One of the things you might notice is that the alcohol we have here has 2 phenyl rings. You might recall that generally when we do a Grignard reaction on an acid derivative such as an ester, we generally add 1 alkyl group from the Grignard twice. And so the hint here is that this phenyl ring probably comes from the Grignard. And so we would use a phenyl Grignard reagent, 2 equivalents of it or more, and use an ester that has a methyl group as a substituent on the side of the carbonyl. So that means that we would have this ester, so a methyl attached to the carbonyl, and then some sort of leaving group on the ester. It doesn't matter what R group is on the oxygen, the reaction should work the same. And so these are the 2 components we would need to use in order to make the alcohol we started with. This question asks us to make the following ketone from an acid chloride and a lithium diorganocuprate reagent. Lithium diorganocuprates are Gilman reagents or copper reagents. And so let's think about what 2 components we would use to make the following ketone, and then we'll look at the answer on the next slide. In this question, we want to make a ketone from cuprate reaction on an acid chloride. This ketone is unsymmetrical. It has what looks like an isopropyl group on the right side. It has a phenyl ring on the left side. So we're looking at this ketone. And with the Gilman reagent in an acid chloride reaction, we have actually two options here. We can have the Gilman reagent provide the phenyl ring, or it can provide the isopropyl group, which means that acid chloride can have already an existing phenyl ring or an isopropyl ring on it. And so the two possible answers are we use this acid chloride with a phenyl ring attached, and the isopropyl group will come from the Gilman reagent. Or we could exchange those two alkyl groups and provide the phenyl ring from the cuprate, and then the acid chloride already has the isopropyl group already attached. Acid derivatives react with hydride reagents such as sodium borohydride, and they generally react twice with a hydride reagent. For example, this acid chloride would react with sodium borohydride, whose structure is shown here. One of the hydrides on the borohydride reagent would add to the carbonyl, break the double bond, give us a tetrahedral intermediate, and then the oxygen will reform the carbonyl by eliminating the leaving group, giving us an aldehyde. And then as we know from previous reactions we covered, aldehydes are generally reduced by sodium borohydride to alcohols, so that is exactly what happens here. The aldehyde will react with the hydride, give you an alkoxide intermediate, which then is protonated by acid to give us a primary alcohol. Overall, we have done two additions of a hydride to this acid chloride, and we're able to do that because of the leaving group that we have on it. Now, sodium borohydride is a mild hydride reagent. It can only react with acid chlorides. It doesn't react with esters and amides. Lithium aluminum hydride, or LAH, is a very strong hydride reagent that can reduce not only acid chlorides, such as benzoyl chloride, into a primary alcohol, but it can also reduce an ester into a primary alcohol. And if we have a lactone, it'll reduce it into a diol. In this last reaction, the hydride reagent provides a hydride to this ketone, ester, turning it into an alcohol and also eliminating the alcohol that is attached to the ester. As a result, we end up with two alcohols from two hydride additions. The reduction of esters is very similar to the reduction of acid chlorides with hydrides. It occurs twice, so the H- from lithium aluminum hydride will be added to the carbonyl, breaking the double bond, giving you a tetrahedral intermediate, which then reforms the carbonyl by eliminating the leaving group, similar to what we saw with the acid chlorides. That gives us an aldehyde intermediate, which then gets reduced again. So a hydride will add to the carbonyl carbon, break the double bond, and then that oxygen is protonated by acid to give us an alcohol, a primary alcohol. Amides are a little bit different when it comes to hydride reactions compared to esters and acid chlorides. For example, if we start off with this amide, when we add lithium aluminum hydride, instead of obtaining a typical primary alcohol, which we did with esters and acid chlorides, we get instead an amine. So let's take a look at the mechanism to see why that occurs. So the mechanism starts with a hydride adding to the carbonyl of the amide, breaking the double bond, giving us a tetrahedral intermediate. What differs here, though, in the mechanism compared to the ester and the acid chloride reduction is that the oxygen is actually a better leaving group than the nitrogen. And so as a result, the nitrogen will push it out as follows, giving us an iminium ion, which then gets reduced into an amine. Here's an example of what would happen with a lactam. With lithium aluminum hydride, we essentially remove the carbonyl completely to give us a cyclic amine. In this question, we want to predict the product that will be obtained from a hydride reduction of the following ester with lithium aluminum hydride. As you may recall, when we do a hydride reduction of an ester or an acid chloride, we typically obtain a primary alcohol. So the hydride, in this case lithium aluminum hydride, would add to the carbonyl once to give us initially an aldehyde by eliminating this phenoxy group, and then it would add a second time to give us the primary alcohol we see here, which is benzoyl alcohol. The phenol that you see on the right side is a byproduct from the elimination of the phenoxy group of the ester in the first addition of the hydride. In this question, we want to think about how we will prepare the following amine and ethyl aniline by reduction of an amide with lithium aluminum hydride. The reduction of amides to amines will occur as follows. So if we're trying to make this amine, we want to think backwards of which amide we would use. We would need to put the carbonyl to the right or the left of the nitrogen. And so since there's no possible way we could add a carbonyl here, the only possible place would be on the right side of the nitrogen. So this would have to be the amide we would need to use in order to make N-ethyl aniline. Although thioesters and acyl phosphates are not very common in organic laboratories, they are extremely important in biochemical reactions. Acyl coenzyme A is one of the most common thioesters in nature. Here is an example of how acetyl coenzyme A can be synthesized. It starts off with coenzyme A reacting with this acetyl phosphate compound. The thiol group will do an acyl substitution on this acyl phosphate. It leads to forming acetyl coenzyme A, and notice we have an acetyl thiol ester as a product. On this slide, there's a couple examples of reactions that acetyl coenzyme A undergoes. For example, glucosamine, which has an amino group as well as several alcohols, reacts with acetyl coenzyme A through an acyl substitution to transfer an acetyl group to the amine in glucosamine. So the nitrogen attacks the carbonyl of the thioester to give you an amide in the product. Choline, which has an alcohol, can react with acetyl coenzyme A through another acyl substitution. Choline acetyltransferase helps in this reaction, which is an enzyme. The alcohol attacks, does a substitution, and so now we have an acetyl group on the alcohol forming acetylcholine, which is an important neurotransmitter.